In this video, I'm going to walk you through the calculations on how to figure out the molar mass of butane. This is the table that you will have to fill out in your lab report, and there is a series of images in the lab instructions where you need to download the pictures, open them up, and you will be able to get the mass of the lighter before and after the release of butane in each trial. Note that the mass of the butane lighter after the release of gas, so the final mass after trial 1, will also be the initial mass at trial 2. And final mass of trial 2 will be the same as the initial mass of trial 3 because we're running these back to back with the same lighter. The volume of gas is given to you as well in the lab instructions, and you will put that in here. It's the same for all 3 trials. The water temperature, and we'll get to it in a couple of slides more, but it is also recorded, so there'll be 3 values here. They are slightly different from each other, not a whole lot, but just record the correct water temperature for each trial in this table. The atmospheric pressure or barometric pressure is the same. That will also be given to you, and it's going to be the same for all trials, all 3 of them. So the volume and the atmospheric pressure will be the same for each trial. Then the vapor pressure of water will be slightly different depending on the water temperature up here. So you will have 3 different values for the vapor pressure of water, and I'll show you how to do that in the next slide. The first question asks you to calculate the mass of butane gas that was used in the experiment. To do that, all you have to do is take the mass of the butane lighter before the release of butane and subtract the mass of the butane lighter after the release of butane. So the top number is going to be larger than the bottom number because this is at the beginning of the experiment, and we release a bunch of butane gas into this cylinder, the volume graduated cylinder, and so this is going to be smaller. You need to calculate the difference, and that's going to be the mass of the butane that escaped from the lighter. Now let's take a look at the 3. So I've copied this from the lab instructions. Okay, the atmospheric pressure is given to you as 762 millimeters of mercury, and that will go here. And it's the same for all 3 trials. Trial 1 has a water temperature of 29 degrees, trial 2, 28, trial 3, 27. Now, what goes under the vapor pressure of water here? Well, what goes under the vapor pressure of water will correspond to the temperature that we have up here. For trial 1, the temperature is 29 degrees. That information will be taken from this table. So we find the temperature, 29 degrees, and the vapor pressure that corresponds to that temperature is 30 millimeters of mercury. So that's what's going to go to trial 1 here. Then trial 2, you go to 28 degrees and you write that vapor pressure and so on and so forth. So this is how we fill out the table with all the information that we need. Now let's take a look at part 2 or question 2. It's asking to use Dalton's law of partial pressures and the fact that butane was collected over water to calculate the partial pressure of butane in that graduated cylinder. Now, once we figured out what those values are, this is what you're going to use. We know that the total pressure, according to Dalton's law of partial pressures, we know that the total pressure or the atmospheric pressure is going to be the pressure of butane gas plus the pressure of water vapor, since the butane was collected over water vapor. And therefore, there's going to be a little bit of water vapor trapped with the butane in that cylinder. And because there's a little bit of water vapor in there, it's going to exert a little bit of a partial pressure. So then the pressure of butane is going to be the atmospheric pressure minus the pressure of water vapor. And you can do that for each trial, right? The atmospheric pressure is not going to change, it's the same. But what changes is the pressure of the water vapor, and that's going to be for each trial. So use the vapor pressure that we looked at in the previous slide, right? For trial 1, it was at 30 degrees, at 29 degrees, so it was 30 millimeters of mercury. So this is going to be 762 minus 30 to find the pressure of butane alone. And do that for all 3 trials and get the pressure of butane alone. And that's part 2. Then there's the conversion. So part 3 asks us to convert the water temperature from Celsius to Kelvin. Use this formula. You know the water temperature, so it's 29, 28, and 27. So that, to convert to Kelvin, you take the temperature, the Celsius temperature, and you add 273 to it. So go ahead and convert all 3 water temperatures to Kelvin. And that is because when we use the ideal gas law, which we're assuming butane acts as an ideal gas, we do not use Celsius for temperature when we use this formula. Okay, so go ahead and convert all 3 temperatures. When you're done with that, you need to use the ideal gas law to calculate the moles of butane in the cylinder. So what is this formula? Pressure times volume is equal to moles times R, which is the ideal gas constant, and it's this value right here, times the temperature. The temperature you just get from part 3. R is right here, this value given to you. Pressure is the pressure of butane that you calculated for each trial, 1, 2, and 3 in the previous slide. And the volume is going to be this volume of the gas. Now make sure that this is in liters, right? Because this formula has liters and this is in milliliters. So convert the volume of a gas to liters, right? If you're going from milliliters to liters, you divide by 1,000. And then use the volume of the gas in liters in place of V here. So plug that in. And then the only unknown you have is the moles. So solve for N. N is going to be equal to P times V over R times T. And you do that 3 times for each, so basically for each trial. Then part 5 asks you to calculate the molar mass of butane. Now, here is what you're going to use for the molar mass calculation. The molar mass, as we know, is a mass in grams divided by a number of moles. So here's the mass in grams. You calculated that from part 1. So use those values, those gram values from part 1 to plug in here for the mass in grams. The moles you're going to use from part 4, from problem 4, the previous slide. We just got done talking about how we use PV equals nRT to find the moles for each trial. So use the grams from part 1 in trial 1 divided by the moles from part 4 in trial 1, and you do that 3 times because we have 3 trials. Then in part 6, you calculate the average molar mass of butane. You will have 3 different molar masses from part 5. Find the average of all 3. When you are done with that, it asks you to calculate the percent error between your experimentally determined average molar mass and the reference that is given, which is right here. So reference, accepted value, literature value, they're all the same thing. This is what this value goes right here. Your experimental value is going to be what you calculate in part 6. the average molar mass of butane from part 6. So accepted value or literature value is going to be 58.12 minus the value from part 6 divided by 58.12 and times 100. Once again, make sure that you do this subtraction first and then divide by the accepted value, or put parentheses around this if you want to do it in one step. Otherwise, what your calculator is going to want to do is order of operations. So if you don't have parentheses here, it's not going to do the difference first. It's going to take this number, divide it by that number, and then take the difference. So either put parentheses here and then divide, because parentheses takes precedence over the division, or just hit equal, or enter in your calculator. So do the accepted value minus experimental value, hit enter, that will give you a number, so plug that in here, then divide it by the accepted value times 100 to give you the percent error. And lastly, part 8 asks you to kind of think about why the percent error might be a little large. What are some points that give us an error in the data? Okay, error will come from any measurement that we make. So think about what is measured in this lab, not calculated, but what is actually measured, and where we could go wrong with those measurements. And that will kind of be sort of you analyzing the lab and be able to give ideas on how you can improve.